Hi everyone, so unfortunately the day has finally come. This will be my last lecture for the semester. However, on the bright side, your presentations are coming up soon and I think you will give amazing presentations based on what I've seen so far, based on your progress on the projects in the last couple of weeks. But before we get to your project presentations, let me today introduce Generative Adversarial Networks, or in short GANs. So Generative Adversarial Networks are maybe among the most active areas of research in deep learning right now. One reason is because they are notoriously hard to train, so people constantly try to improve them. The other reason is they can make pretty amazing applications. So there are many amazing, or at least interesting, projects where people use GANs to generate new data or modified data. For example, if you think back of the example I've shown you from the stuff in the news sections where people try to use GANs to generate new chair designs and so forth, or face images. So today we will talk about GANs in a more general way. We will just introduce how they work and what makes them so interesting and how they are different from other types of neural networks, namely that there are two subnetworks that are competing against each other. And then we'll also try to reserve some time for code examples again. So I'm trying to keep the number of slides relatively small and then also walk through some code examples because again, GANs are pretty interesting, but also kind of complicated, more complicated to what we have covered so far. So we'll maybe take some time to take a look at how we can implement them. And with that, let me get started with the last lecture for the semester. Today, it's time for another brief introduction. The reason is GANs, that is a very big topic. We can spend the whole semester just talking about GANs. So I'm trying to cover the topic Generative Adversarial Networks in one lecture, which is maybe a little bit short, but I hope at least it's inspiring. And after the lecture, if you're interested, you can dig in deeper into GANs and maybe look up some cool applications, implement them yourself, maybe read some papers for improving GANs and so forth. So, like always, the lecture material is available on GitHub, which I recommend obtaining before you watch the video, so you can take notes on your slides. Before we start with the main lecture, let me show you a cool video as an application of a GAN. So I think this video looks super cool. So they took a video of an existing horse moving in that video, and then they projected the pattern of a zebra onto the horse. And I think this looks pretty realistic. I mean, this kind of looks like a zebra, right? So that is one cool application of a GAN. And how the researchers did that is they used a so-called cycle GAN. We won't go into too much detail of how a cycle GAN works, but after this lecture, I think it should be pretty accessible, the paper here. So if you're interested, you can read more about cycle GANs here in this paper, which is very nicely written and very intuitive, not too much math. And also I have to say that it's a pretty cool technique overall. I have also used that in other projects, for example, my privacy net project. So also there's a PyTorch implementation if you would like to play around with that code. And of course, this is only a very short clip from the original video. So if you want to see the longer version, you can also check out this YouTube video here. So, but one more thing, I just see I added a note to ask you a question here. So the question would be, why does the model change the background as well? I mean, it doesn't only change the horse inside the video, but also the background. So you can see, if you would watch the video again, pay attention to the background. Yeah, you can see that the background is now more brown than before. And as a question for you, why do you think the background changed also? Why did the color of the background change? So maybe if you have a good hypothesis, you can post that answer on Piazza and we can discuss that further. And also one more thing to say about that is what's impressive about this project is that they used an unpaired approach. So before, what researchers usually did is when they wanted to map some textures onto an existing image or object, they needed to do a paired approach where you had the same picture with and without the styling in the texture styling. So when they wanted to train neural networks, they had to have the images prepared such that the same object was oriented in the same way, in the left and the right. Here, this entirely works on unpaired images, which means you just need a bunch of horses and a bunch of zebras, but they don't have to be in the same position. And then the network will automatically learn to map the pattern of the zebra onto the horse. Also, by the way, that would be working backwards as well. So you could also have a video of a zebra and the network would be able to map the horse pattern onto the zebra. So basically removing the stripes. So in any case, if you have a good hypothesis why the unpaired image-to-image translation here produces also the brown backgrounds, just post this question or the answer to this question on Piazza, and I will be looking forward to check this out later. Next question, who is this person? So if you don't know the answer, if you don't know who that is, maybe stop the video at that point and think about it for a couple of minutes and then come back to the video. Of course, I was just kidding, and I hope you were not thinking forever, because this person doesn't actually exist. So this is a picture from this website here. Every time you refresh the website, you will see a new face image, but all of the face images here are generated by a GAN, so they don't actually exist. So they are really entirely made up by the GAN. And this is based on a so-called style GAN. You can find the details in that paper here. And we won't go into too much detail of how the style GAN works, but at the end of the lecture, I'm including code that I implemented for generating new face images using a deep convolutional GAN. And maybe after the lecture, you might be interested in generating such high quality images. So you can then maybe read the paper here about the style GAN, modify my code, and also try to generate higher quality faces. Here's another website that took the idea from the previous website and turned it into a small game where the user or the visitor of this website is asked to click on the person who is real to see whether you can guess whether the person is real or not, which is, I think, a pretty impressive application of neural networks, because I'm actually not able to tell which person here is real. I mean, the question is, can you tell? So I actually set up a small Google form survey here. So maybe let me know what you think, which person is real or which face image is real, and then I will show you the results later on Piazza, so we can have a small survey to see how many of you are able to guess right here. Okay, but now let's get to the main lecture. Let's talk about GANs and how they work. So I structured the video or the lecture into 4 parts. So the first one is just explaining what GANs are, the main idea behind GANs, so the architectural overview. And then I will show you how we can train GANs. So the second part will be on GAN training, looking at the loss function and how we minimize or optimize the different objectives in a GAN. And then we will look at some GANs in practice, where I implemented several GANs and will walk you through some code examples. And then finally, because this is like a brief introduction, I will give you some more pointers. So when you are finished with that lecture and interested, you can learn more about GANs afterwards. So the original purpose behind GANs is to generate new data. So the idea is that we have a training set distribution that is kind of intractable. So we use a model, a machine learning or deep learning model, that can use that training data to generate new data that doesn't exist in the training data yet. Usually people use GANs for generating new images, for example, the face images I just showed you, but the general concept is applicable to a wide range of domains. However, I would say it's just easier to work on face images or in general in images, because in that case we can look at the results and as a human can say whether the results look good or not. If you, for example, generate some numbers in a table or something like that, it's maybe not clear how realistic the numbers are. But for humans, it's kind of easy to tell whether the results look good or not. And the reason I'm saying that, why the human is kind of important in that loop to look at the results, is that we don't really have very good metrics yet for measuring how good a GAN is. There are several methods out there, existing methods, but of course they are not as good as having humans looking at the results. So some of the, I would say, advanced research projects, they still use humans to evaluate results. So it's set up Amazon Turk experiment or some other survey software where people are shown the different images, similar to what I've shown you previously with a person who doesn't actually exist. And then they ask people how confident they are that these images are real or generated, and that is then used for evaluating the performance of the GAN. So In addition to that, what a GAN does, it's learning the training set distribution. So it can then generate new images that have never been seen before, which I just mentioned. And there are other methods for generating new things. For example, if you remember the RNN lecture where we had RNNs, or also if you know that from other statistics courses, autoregressive models, they generate one thing at a time. So the RNNs were generating text at a time, or autoregressive methods, for example, for time series modeling, they are generating one data point at a time. The difference between that and GANs is that GANs generate the whole output all at once. So fundamentally, GANs work very differently from RNNs. In GANs, there is no time dimension necessarily. So we have a GAN that is generating the whole output, the whole image all at once. And that is mainly the difference between RNNs and GANs. And I would say GANs for text are really not that good yet. I mean, we don't have really good methods for generating text with GANs, but it's also not necessary to, I would say, apply GANs to text analysis because we have RNNs and we also have the transformer models that I talked about last lecture. So really, the GANs, I would say, are most useful for image data. Yeah, believe it or not, the original Generative Adversarial Networks paper was published 6 years ago. It's a long time and it remains a very popular topic in deep learning. So the original paper by Goodfellow and co-authors is also available on arXiv here. If you're interested in reading more about GANs, or if you're interested in having a written introduction to GANs, I really recommend that paper because it's the first one and the basic introduction to GANs. So let me then, based on that paper, walk you through how GANs work. It's simple. I'm not showing you the full architecture yet, only one part of it. So here we have a real image, or just a real training example. Let's call that X. And we have a discriminator, which is a neural network. It could be a multi-layer perceptron, but it can also be a CNN. So basically any type of neural network. And it's also, what's key about that is it's a binary classifier. That means it is classifying based on two possible classes. In this case, the two classes are real image and the other class is fake image. So the discriminator returns a confidence score of how likely it thinks the image that it receives is a real image. And then you can get the probability for fake image simply by 1 minus p real, right? So in that case, we only need one output node for the discriminator, and the job of the discriminator is to distinguish between real and fake images. So here I added some more components to the previous figure. So previously what I showed you was we had a real image X, and that image went into the discriminator. And the discriminator returned a confidence score, like how likely it is that the image is real that came into the discriminator. And now we have a second image, let's call that new image, or X prime. And this is an image that has been generated. We also say sometimes it's fake image because it's not actually in the training set, it's a generated image. We can also say synthesized. These are all different words that mean the same thing here. So this is an image that comes from a generator, which is also a neural network. Could be, for example, also a multi-layer perceptron or convolutional neural network, CNN. And if you think back of last lecture, the autoencoder, think about how the autoencoder worked. So we had an encoder part. So the encoder took an input image, for example, a face image, and was producing a vector, let's call that vector z. And then from that vector we had a decoder, and that decoder was also producing an output image. So it was going from z to the output image, and then the objective was to minimize the distance between those two in hope that the autoencoder encoder network will learn how to compress and reconstruct images. So here, just forget about the encoder for now and just focus on this part here, the decoder part. So the generator is essentially a decoder. So the generator receives a vector, and then from that vector, it generates the image. In this case, the vector here is just random noise. You can sample that from standard normal distribution with zero mean and unit variance, or you can also use a uniform distribution and just sample from that one. Doesn't really matter that much in practice. So the key idea here is that this is a random noise vector, and the generator learns to generate a new image from this random noise. And then the new image here goes into the discriminator, and the discriminator has to tell whether it's real or fake. So the discriminator is trying to learn what makes a real image different from a generated image. And the generator learns how to produce images that can fool the discriminator. So the generator wants the discriminator to make a wrong prediction, and the discriminator wants to make a correct prediction. So there's some adversarial game going on here. So like I said, the discriminator learns to become better at distinguishing real from generated images. So it learns how to do a better job at the prediction. And the generator, in turn, learns how to generate better images to fool the discriminator. So this is why we call that adversarial game. So there's an adversary. The generator is basically the adversary of the discriminator, and the discriminator wants to make a correct prediction, and the generator tries to fool it. So there are two contradictory goals that are going on here. So you can think of it as two players competing against each other, and both players want to win, and then they compete against each other by this little game here, the GAN game, if you will. By the way, I'm saying sometimes GANs and sometimes GAN. So is it singular or plural? Do we say generative adversarial network, generative adversarial networks? So in the original paper, Goodfellow et al. So Goodfellow and colleagues, they used the term generative adversarial networks with an S at the end to refer to this one architecture. And the reason why it's networks is because there are two subnetworks. There's the generator and the discriminator. So there are adversarial networks in this one model. And this is also abbreviated as GAN in the paper. So if you say GAN, it means generative adversarial networks. And nowadays, it's also common to just say generative adversarial network for some reason. So some people refer to the one model as generative adversarial network without the S here. However, doesn't really matter in practice. And I will try to have the convention. If I say GANs, I mean multiple generative adversarial networks. And if I say GAN, I mean one generative adversarial networks. It sounds a little bit weird to say one generative adversarial networks because, it's a plural here, so it gets a little bit confusing. So please forgive me if I'm not super consistent, but I just wanted to note why I'm sometimes saying GAN and sometimes GANs and where this comes from. Since we are already talking about terminology, let us take a look at this paragraph here that I found in a paper by Lipton and Steinhardt. So in this paragraph, Overloading Technical Terminology, the authors also highlight the kind of problems in deep learning, that in deep learning we sometimes use terms from, let's say, statistics, but we mean something different if we use them. So in that case, they say, consider the case of deconvolution, which formally describes the process of reversing a convolution, but is now used in the deep learning literature to refer to transpose convolutions, also called upconvolutions, as commonly found in autoencoders. So remember from last lecture, I called them transposed convolution, and I mentioned sometimes they are called deconvolutions. However, they are not technically the same thing. So traditionally, deconvolution means something very different. Some deep learning libraries, however, they use the term deconvolution to refer to transpose convolutions. Anyways, long story short, what I'm also trying to say here is the transpose convolutions will become more, or again, useful. So last time we looked at them in the autoencoder, decoder part. Now we are also using them in the generator of a GAN model, where that only applies, of course, if we use a CNN as a generator. But again, the transpose convolutions will be useful again. And related to that, also, you may wonder where the term generative comes from. If we talk about generative adversarial networks or GANs, we have the generative in that word or in that term. So where does it come from, and how does it fit to in the context of other statistics classes that you've maybe taken before this class? So also Lipton and Steinhardt have a section on that one to answer that question. So I'm not going to read this here, but the general idea is the generative part in the GAN comes from the fact that the model can generate new data. So it's in a way consistent with generative models in statistics. So here the discriminator would essentially learn implicitly the distribution of the training data. So it does learn PX, so the distribution of the training data. However, vanilla GANs cannot do conditional inference. With that, for example, you cannot sample value of pixel at position 1 given, let's say, the value of pixel 2 and so forth. So in that way, it's kind of limited. And also sometimes students ask me what I mean by vanilla when I say vanilla something. Vanilla usually means the plain version of something, or the, I would say, unmodified or basic version of something. For example, sometimes people say vanilla Python, that just means the regular Python. So it can also mean like the regular version of something. Just in case you were wondering what the term vanilla means when I say something like vanilla GANs, because there are maybe GAN models that can do conditional inference. It's just not like the normal version of GANs. But anyways, enough about terminology, because yeah, terminology is just a distraction sometimes even. So let us get back to the main parts of this lecture, and let's talk about GAN training now that we have the main idea behind GANs. So the big question now is, when does a GAN converge? So we have, if you recall, this adversarial setting where we have a discriminator. The discriminator receives either a real image or a new image. So the new image is the generated or fake image, which comes from the generator. So the generator wants to become better at generating images that look real. So it wants to fool the discriminator. So it wants to fool the discriminator, D. And the discriminator wants to become better at distinguishing real images versus generated images. So it wants to, in that way, it wants to beat the generator by uncovering its generated or fake images. So there's an interplay between two adversarial objectives. The generator wants to become better at fooling the discriminator, and the discriminator wants to become better at detecting that it's being fooled. So when does it converge? When does the GAN model converge if we have these two dual objectives? So the answer is that there will be an equilibrium, and this equilibrium is the state where both generator and discriminator are kind of happy. So if one changes, it's kind of detrimental to the whole system. So there's a nice interplay between generator and discriminator. So how does the loss function, objective function, look like in the case of a GAN if we have these two objectives? So here is the GAN objective, and the GAN objective that we want to optimize is a so-called min-max game, or also called zero-sum game in the field of game theory. So sometimes people also call it mini-max. And what we have here is we have a minimization and a maximization problem. So what we want here is to minimize some objective of G, where G is the generator, and maximize some objective, part of this objective for the discriminator, D. And as you can see, there are two parts here. There's one part that only depends on D, and the second part depends on D and G. So we have a G here and a D here. And we are going to take apart this equation now and look at it in two parts. So first we will look at only this part, and then secondly we'll take a look at the right part here. Let's look at this objective here just from the perspective of the discriminator. So we are only looking right now at this maximization part, the discriminator part. So because this is a maximization problem, we have to use gradient ascent here. Recall in previous lectures we always wanted to minimize a loss, and when we wanted to minimize it we took steps into the opposite direction of the gradient. And we called that stochastic gradient descent, where we took steps into the opposite of direction of the gradient. Because right now we don't want to minimize something, we want to maximize something. We don't use stochastic gradient descent, we use stochastic gradient ascent, for example. Okay, so let me erase that because I will later refer back to the text here. So what we have here is the two parts I talked about earlier. We have the left part that only involves the discriminator, and we have the part that involves the discriminator and the generator. Let's only take a look at this left part first, which is this part, and then we will take a look at this right part here, which is this part down here. So what I'm writing down here is the gradient of the loss with respect to the weights of the discriminator. So D here means the discriminator, so we are only updating the weights of the discriminator. And I just see I forgot the L here because we compute the gradient of the loss with respect to the weights. And this is only for updating the discriminator. So if we want to implement the update in code, we would use, for example, stochastic gradient ascent, and optimize this. And when is this optimized? It's when these terms are maximized. So we want to maximize these terms. And now let's look at the left part. So what we have here is log D of xi, where I is the ith training example. I should also say we have the sum here replacing the expectation because it's like a discrete case where we have the training set. So we're only talking about the training examples here. And so the output of log D xi, this is the prediction on an image x, is a value between 0 and 1, because recall the discriminator is a binary classifier. So let me write this here. So what it outputs is the probability given, given that we have an image xi, the probability that this is a real image. And this is a value between 0 and 1. So that's what the discriminator outputs. When is that maximized? Let's look at some values that we can put into the log. So what happens if we start maybe at the smallest value, let's put 0 in here. So that's the smallest value here, right? So if we put a 0 in here, that would be minus infinity, right? And then if we have a log, let's say 0.5, so you recall that would be always equal to a random prediction. That would be minus 0.69, I think. And then lastly, if we have a log 1, that would be exactly 0. So when is this part here maximized? It's when we have the highest value here, right? And the highest value is the 0 based on all the possible inputs. The input domain would be 0 to 1. If we input a 1 here, we get 0, which is the highest value here because these are negative values. So what we want is, we want for this part a probability close to 1, which translates to a discriminator that predicts well on real images. So assuming it gets a real image here, the objective here is maximized if it makes a correct prediction. Okay, so that was the left part of this equation. Now let's take a look at the right part here. So we're talking about this part here. A bit messy, so I cleaned the slides a little bit so that we have more space for explaining the second part here. So we just talked about this part that we wanted to maximize in order to maximize this whole thing for the discriminator. Now we are going to take a look at this part, which corresponds to this part here in this equation. So before we wanted the discriminator to predict well on real images. That means outputting a probability close to 1 if an image is real. And similarly, we do the same thing now for fake images. So first of all, let's take a look at this right term. What's going on here? So we have again a discriminator here. And now it receives the generated or fake image, which we previously called x prime. So that is the generated or fake image, because that comes from the generator. So the generator takes in a random vector z. So I stands for the ith iteration in the training loop here in this case. And G, the generator, produces X prime, the fake image, and the discriminator has to predict now whether it's real or not. So now let's take a look at the log again. What we have here is a 1. So we have log 1 minus something. So if we put a let's say a 1 here, what happens is the whole term becomes 0, and the log of 0 is again minus infinity. So that is the opposite of maximizing something, because it would be a very small or a very negative value. So that's exactly the opposite of what we want. So what we want is for this term here to become 1 again, right? So that's the highest value we can get, and we can get that value by putting a 0 here. If we put a 0 here, this whole term becomes 1. So maybe it's not that clear. Let's do it like this. Put a 0 here, this term becomes 1. This becomes 0. And because we have then log of 1 equals 0. And this is then also the maximum value we can get for the right part here in this equation. So by having a 1 here and or having the discriminator outputting, so I should say if we have a 1 here for the log, and we have output of 0 here for the discriminator predicting on the fake images. 1 here, the discriminator outputs a 1, and the generator outputs a 0. Then this whole objective is maximized, because this whole term will become 0, and this whole term will become 0, and that is the largest value we can obtain in this case. So we want the discriminator to output 1 on real images and output 0 on fake images. Okay, so that is the discriminator in the generative adversarial network. Next, we are taking a look at the generator. So in the next slide, I'm going to show you this part. Let's take a look at the objective again, now from the perspective of the generator. So in the case of the generator here, we want to minimize something. So we want to minimize this whole objective. And now, since it's a minimization, we can use gradient descent. So before we had gradient ascent because we wanted to maximize. Now we want to minimize, which is why we can use gradient descent here. Okay, so what do we have here? If we look at the left part, there is actually no generator. So we can just cancel this from our mind right now, because we are not updating anything with respect to this term, because there's no generator involved. For the right part, we have the same setup as before, where we generate an image here. So this is X prime, the image X prime, which the generator generates from Z. And that is given to the discriminator to make a prediction. So again, we want to compute the gradient of the loss with respect to the weights, but now it's the generator. So the same basic setup. The only thing that changes compared to before is what value we want the discriminator to output. So before, the previous slide, we had a 0 here, and the 0 maximized this term. Then this whole term became 0. Now, we want the discriminator to make a wrong prediction, because remember, the job of the generator is to fool the discriminator. So we want the discriminator to predict with high confidence that something is a real image, although it's generated. So this is X prime, this is the generated image, but we want the discriminator to think that this is actually X, a real training set image. In order to achieve that, or we learn this objective to achieve that, and that is the minimization problem. So the part where the discriminator makes a wrong prediction is when the probability is close to 1, because 1 means that it's very confident about X prime being real. So that would be this part where it returns a high probability, thinking that this is a real image. And so what happens if we put a probability close to 1 as the output of the discriminator? So if we make the discriminator learn how to output high probability scores, so let's just plug in the numbers. So we have again a log, and then this 1 here, and then say minus, and then we want this one, or the whole discriminator, to output a value close to 1. So let's assume it's 1. What happens is that the log of 0, that we have a log of 0 here, and the log of 0 is of course minus infinity. So in that case, we minimize this whole objective here by putting a probability close to 0 here, close to 1 here, such that the log will be 0, which will then cause the whole objective to be minus infinity, or very small, infinitely small in fact. So by that, by just having the discriminator predicting a probability close to 1, in this case, we'll minimize this objective here. So that is the part about the generator where we want to fool the discriminator to make wrong assessments about the generated images. So here I have a screenshot from the paper, the original GAN paper, and I just see here it's called Generative Adversarial Nets. Previously, when I showed you the paper, I called it Generative Adversarial Networks. So why nets and networks? I think in the Europe's version, in the published version at the conference, they call it nets. In the archive version, they call it networks, but it doesn't really matter. So here, this is the general algorithm for the GAN training. So what we have here is mini-batch stochastic gradient descent, and there's a loop over the training iteration, so how many updates, how many iterations it runs. And then there is a block for, here there's a block for updating the discriminator. And there's a second block for updating the generator. So let's take a look at what's going on here. So first of all, we notice there's k steps here, and that means we would update, or we can update the discriminator multiple times before we update the generator. So here the discriminator may be updated multiple times before there's one generator update. And of course we can set k equals 1, and then we have an equal number of updates for the generator and the discriminator. So for the discriminator, we sample a mini-batch of noise samples. So these are the random vectors we draw from a standard or normal distribution or a uniform distribution. And we also sample a mini-batch from the original training set. So here, data generating distribution means the training set. And yeah, we update the discriminator by running stochastic gradient ascent. So this is ascent, which means we maximize something here. We maximize this term we previously talked about. And then now for the generator part, this is using a stochastic gradient descent. So we are minimizing this term. This is what we talked about in the previous slide. Okay, so yeah, that is the overall training algorithm. So we update the discriminator one or more times, and then we update the generator, and then we go back and update the discriminator again, and then the generator, and so forth. We can come back to the original question: when does the GAN converge? So we have this mini-max setting here, the min-max or zero-sum game that we discussed in the previous slides. So it converges when it reaches the so-called Nash equilibrium, which is a term from game theory. In general terms, the Nash equilibrium in game theory is reached when the actions of one player won't change depending on the opponent's actions. So we have a system with two players competing against each other, and both are happy with the current outcome in a way. So no player wants to change a certain strategy because it's currently in this optimal state, in this Nash equilibrium. And in the concrete example of the GAN, that means that the GAN, or the generator, produces realistic images, and the discriminator outputs random predictions. So the discriminator is not able to tell whether the GAN or the generator produces realistic images or not, and that would be the case when we have reached the Nash equilibrium in that case. Here's another figure from the Generative Adversarial Network paper. And here in this figure, they are illustrating the process of reaching the Nash equilibrium. So recall, the Nash equilibrium is the state where the generator produces realistic looking images, and the discriminator is unable to tell whether a given image is real or not. So it outputs the 50% probability in both cases. A lot of things going on in that figure, so let's unpack that step by step. So the first thing to notice is that there are 4 steps, A, B, C, and D. And before we can start talking about step A, let's annotate step A. So going through the figure caption, what we can see is there's a discriminative distribution, D, the blue dashed line. So that is the distribution of the discriminator, or rather what the discriminator outputs. I think they forgot the y-axis here. So for the discriminator, let's put a y-axis here, and this would be, let's say here, the output where the probability is 1 for predicting real, and the probability for real is 0 here at the bottom. And let's then further to take a look at the caption to see what the other elements are. So there's a data generating distribution in black, that would be this one. And data generating distribution here means the distribution that from which the training set was drawn, for example. So in practice, usually we have a training set, we don't have access to the whole distribution. So let's just call that, so it's more intuitive, training distribution, for example. What else do we have? We have the generative distribution, the green solid line. So that would be the generator. So, or rather the distribution generated by the generator. So the fake data. So let's call it the fake data. And then we can call the training data the real data. So what other elements do we have here? So there's also a second part to this plot where we have a z and an x. So z is the distribution from which we sample the random vectors that go into the generator. And here we cover the whole breadth, basically, that we just sample from this distribution. However, then the values sampled from this distribution are mapped to a narrower region on the data generating distribution. And this narrower region corresponds to the region where we have the highest density of the generative or generated data. So it's mapping from the random distribution to the point where we have the generative distribution, the fake images. So it's just saying this is what the generator performs, so what mapping it performs. It basically doesn't cover the whole training set distribution. The whole training set distribution would be this part. It maps to a narrower region of this distribution. And the goal would be, of course, to map to the region that corresponds to the sample, to the highest density of the training data, or the highest density of the data generating distribution. That would be the goal. So we want these things to map here into this region. In any case, so that is not the main point here. The main point is here the process of how the GAN reaches convergence, so how it may look like in practice. So what they say here for A is that A is a system that is near convergence. So we have for, let's say for this region, we have a discriminator that outputs occasionally the highest probability that this is a real image, which is good. So this is what we want. We want this discriminator to say these images are real. I mean, this region in this region here. So that is good. Also, it's quite good that it outputs something close to 0 in that region here. So that means the discriminator is performing quite well. And also the generated distribution is not too far away from the real training set distribution or generating data distribution. So this is a system that has almost converged. It's not quite there yet because the discriminator still fluctuates between 1 and 0. And also the generated distribution, or the data generating distribution, is different from the generated data. So it's not quite the same. We want them to overlap. So in step B, let's take a look at step B now. In step B, the inner loop of the algorithm D is trained to discriminated samples from the data, yada, yada, yada. So that means the discriminator is updated here. So what happens is, after this step, we update the discriminator. And what we can see now is that the predictions are more confident. So we can see it's not fluctuating anymore because that's after we trained it on the current state of the generator. Next, we update the generator here. And what we can see is based on the discriminator now, I mean, the job of the generator is fooling the discriminator. So what the generator will do is it will try to make the output or its output closer to the data generating distribution, closer to the training data set. So what it will do, it will move the generated data distribution closer to the real data distribution. So you can see here they overlap quite more substantially now. So that is after updating the generator. And then assume we have done several steps. So they perform several steps, imaginary steps, and then reach the state D. And this is the step where we have the Nash equilibrium. So in this step, we have a discriminator that is unable to differentiate between the two distributions. So it outputs a probability of 50% because it doesn't know whether some data point is real or fake. Why doesn't it know whether it's real or fake? Because it's impossible to tell if we have reached the optimal state. Because as you can see now in this optimal state, the generated distribution and the real data distribution, they overlap completely. So that would be the state where the generator is most happy. In a way, it's not most happy because it can't fool the generator anymore on the generated images. It does a 50% prediction instead of, let's say, 0 confidence, but it's a state where we generate the optimal images and the discriminator is unable to tell. So that's basically the best outcome for both, for the combination of both. That is where you don't want to change the discriminator and you also don't want to change the GAN. This is exactly the equilibrium that we want to reach by our objective that we talked about in the previous slide, the minimax. That was a basic illustration of the GAN training process. In practice, training GANs is actually pretty hard. I mean, not that hard, but definitely harder than training a regular multilayer perceptron or convolutional neural network, because now we have two things that we have to optimize, the generator and the discriminator. And one of the biggest problems is that the losses can oscillate, so they go up and down between the generator and discriminator, and they never really reach a state where they reach that equilibrium we talked about. Another problem is the so-called mode collapse, and that means that the generator produces examples, here training examples of a particular kind only. So that means that, for example, if you have an MNIST data set, the generator maybe only generates images from a certain number, let's say the digit 8. It doesn't consider any other numbers, only generates numbers from one particular class, for example. So that is a case of mode collapse where it only produces very narrow region of the training set. Another problem is that the discriminator is too strong, such that the gradient for the generator vanishes, and the generator can't keep up with the discriminator, so it kind of never really gets to the point where it learns producing some useful images, and we will take a look at that in the next slide actually. And another problem is the discriminator becoming too weak or being too weak. And that means that the generator produces non-realistic images that can fool it too easily. And if the discriminator is fooled too easily, then the generator doesn't have the motivation, if you will, to become better. So if the discriminator is easily fooled, the generator doesn't even have to put much effort into generating images. And then if that's the case, we will never get a GAN that can generate really good images. But that problem is, I think, relatively rare. Usually what I have is that the discriminator is too strong. So that is a case I often see in practice. Sometimes I find mode collapse and of course something where I have an oscillation between generator and discriminator losses. But the last point, I would say this one is relatively rare, but it can happen, of course. Let's revisit the point that I made on the previous slide, where the discriminator is too strong, such that the gradient for the generator vanishes and the generator can't keep up. And that is a problem that often happens early on during training. That is when the generator has not really learned yet how to generate good or realistic data. And there's a fix that they mention in the paper, which we will talk about now. How can we make the generator update more quickly early on during training? How can we provide it with a stronger gradient? So for that, let's take a look at the original formulation here. So let's call that the original setting. And remember, in that original setting here, what we wanted to do is we wanted to minimize this following part, which is the generator part, using gradient descent. So that was the part, the gradient of the loss with respect to the generator weights that we wanted to minimize. And that is, or minimizing this means that the discriminator is successfully fooled, because what we want is the discriminator to output something close to a 1. And again, the discriminator output is a probability that it thinks a given image, x prime here, would be a real image. So x prime, that is the generated image here. So we want to fool it, we want to think, or we want to make it think that this is a real image. However, early on during training, what happens is that this part will be more close to 0 because the generator hasn't really learned yet how to generate realistic images. So now, why is that a problem? So the problem is the gradient in that case will be very small. So why is that? Let's for that take a look at what we have here, that equation here, or that expression. So if we would compute the derivative of that, let's call that, or let's say log 1 minus, let's call that whole thing here just x. What we have then is log 1 minus x. What is the derivative of that? So for that we would use our good old friend, the chain rule, and then have the outer times the inner derivative. The outer derivative is the log, so the derivative of log x is 1 over x. So in that case, the derivative of log 1 minus x for the outer part would be, so let me do the inner part, it's getting confusing first. So it's just the inner part from the chain rule, so it's the derivative of that one. And the outer derivative would be 1 over whatever is inside the log. In that case, it's 1 minus x. And then if we solve the upper part here, if we compute the derivative of that part, the derivative of, so we can use the sum rule, the derivative of that one goes away. And then the derivative of the second part is, minus 1. So what we get here is the dx of log 1 minus x, that should be minus 1 minus x. Okay, so now what happens if we have something that is close to 0 and put it in here, so that whole thing will become minus 1, right? So in that case, we have a very relatively small gradient. We can increase the gradient by applying simply a trick by dropping this term here and using gradient ascent to maximize this. So remember, what we have is, what we want is a 0 here. And if we have a 0 here, we have now log 0, which would be minus infinity. And also when we look at the, so we want to maximize that now. We want to bring that close to 1, which means that what we want is log 1, which will be 0. So we want to maximize this from minus infinity to 0. And here we have just log x in it, if you want to write it like that. Log x, the derivative of log x is 1 over x. So we will have a much stronger gradient if we have something that is close to 0 in that case. So if we have something close to 0, that will be a very large term. We can't have exactly 0 here, because then the problem would be we would be having a division by 0 error. But by this simple trick, by just dropping this term and replacing gradient descent with gradient ascent here, we can actually fix this slow learning problem when the discriminator is too strong in the beginning. So that is one little trick we can apply. So before we go to the code examples, let us briefly summarize what we have covered so far. And if that is still confusing, I think it will become more clear after we walk through the code examples. So, but for now, let us just still summarize what we have so far, because that will kind of motivate the code examples. So for the discriminator, we have the following setting, that we want to maximize the prediction probability of classifying real as real and fake as fake. So what we, for example, want to do here is we want to maximize a likelihood. That's actually, I call this prediction probability, but you can think of it as a likelihood, because we are not changing the probability of the data. We are just changing the outcome of the discriminator. So we can use the maximum likelihood approach here. Instead of maximizing the likelihood, we talked about maximizing the log likelihood when we talked about logistic regression. And that is the same as minimizing the negative log likelihood, right? So in the context of logistic regression, we talked about this approach, and we used the cross entropy function in PyTorch. Why are we talking about minimizing now? That is because in PyTorch we also use stochastic gradient descent, or ADAM, which is a variant of stochastic gradient descent. And we don't want to change our optimizer, which is minimizing something. So we just, in this case, reframe the maximization of the log likelihood here into minimizing the negative log likelihood, which is the same as minimizing the cross entropy. So that is what we do for the discriminator. When we implement it, we just simply minimize the cross entropy of the predictions. For the generator, we said in the beginning we minimize the likelihood of the discriminator to make a correct prediction. So we want to predict fake as fake and real as real. And this can be achieved by maximizing the cross entropy. So now the key here is we want to minimize the likelihood. So here that means that we want the discriminator to make a wrong prediction. So we don't want it to predict fake as fake. We want to minimize the likelihood that it does actually predict fake as fake and real as real. So we want to fool it here. But then we learned that this minimizing of the likelihood doesn't work very well in practice, because we have the gradient issues where the signal is very weak in the beginning of the training when the generator is still weak and the discriminator is too strong. So in order to fix that, we turned that into a gradient ascent problem, where we dropped one term and maximized the likelihood. However, again, in PyTorch we have SGD and ADAM. So how can we turn what we had on the previous slide, the trick that we applied, into a minimization problem? And we can do that by just simply flipping the labels. So we flip the labels of the classes, of the real and fake classes, and minimize the cross entropy. And that forces the discriminator to output high probabilities for fake images if an image is real, and a high probability for real if the image is fake. So you can think of this as just a regular prediction, a classification problem where we use the cross entropy that we minimize. However, we have the labels now flipped, so we force the classifier in this case to make a wrong prediction. And this is also for the generator part. So the generator will learn how to fool the discriminator just by flipping the labels. And I think that will become more clear if that's a little bit confusing right now if we look at the code examples now. So let's now take a look at the code examples, which we call GANs in practice. And I prepared the code examples because we don't have that much time left in this lecture, in the lecture here itself. So I will walk through the code examples in the slides and annotate a little bit. But the full code examples are also, like always, available on GitHub if you want to execute them later. So let me walk you through the code examples. I'm not showing you the whole notebook because there are a lot of distracting parts like the data loader and so forth. So here we are only going to focus on the main parts that are important for implementing a GAN without all the boilerplate code. So what we are doing here in this first step is we're setting up the class label vectors that we are going to use. And here I'm talking about the class label vectors for the real and fake images. So for the real images, we assign the class label 1. So every image tagged with a 1 is a real image. And we use zeros for representing fake images. So here I'm just creating two vectors, and maybe it's a little bit confusing what that means. That was just computing the size of the mini batch. So you can think of this part as mini batch size. So maybe just think of it as mini batch size. So I'm creating two vectors here with class label for training, one with the class labels for the real images and one for the fake images. Next, I'm going to generate the new images from random noise. So I'm going to use the generator. So that is a generator model I implemented. I'm not showing you the forward method here, but there is a forward method, and it is very similar to the decoder that we had in the autoencoder. And this one is generating the images from the vector z. And again, let's maybe draw that. Again, this is similar to the autoencoder. So in the autoencoder, we had this hourglass. Maybe it's not quite clear here. We had this hourglass shape. And in the center, we had a z vector. And here on the right side, that was the decoder. And the decoder was generating the image from this vector here, from this z vector. And here, instead of producing the z vector with an encoder, so in the autoencoder we had an encoder part. In the GAN we don't have an encoder, so we don't think of this one. But the z vector has to come from somewhere, right? So for that we use a random distribution. So we can use a random uniform distribution, but you can also use a standard normal distribution. And yeah, we are drawing a random vector from this distribution. Here it looks maybe a little bit weird because I have this part and then there comes this part. So remember, everything with an underscore in PyTorch means modifying something in place. So I'm first just generating a placeholder vector. So this is just a placeholder vector that has the same size as the mini batch size. So again, I have this target size here, which is the mini batch size. And then I'm replacing it with values from a random distribution, for a random uniform distribution. And maybe one more thing to say here is that we have a latent dim. So that is the dimensionality or the size of the vector z, because also I have to choose the size. Similar to the autoencoder, this has a size that we have to specify. Usually you don't want to make it too big or too small. It's a little bit hard to recommend a rule of thumb. You have to experiment a little bit with that. But you don't want this to be bigger, for example, than the number of pixels in the output image, of course. So that should be usually a relatively small fraction of the output image that you expect. Okay, so that is step 1, creating the class labels, and step 2, generating our fake images. Next, let's talk about the generator loss. The generator loss was only consisting of one part where we wanted to minimize the likelihood that the discriminator makes a correct prediction. And we can achieve that by maximizing the likelihood that the discriminator makes a wrong prediction. So that was flipping the labels that we discussed before. And maximizing the log likelihood, so we would use for that gradient ascent, but like we talked about before, using or maximizing something is not really convenient in PyTorch because we use SGD. What we can do is we can just minimize the negative likelihood, which is then just using the cross entropy, minimizing the cross entropy. And in the binary case, we have also the binary cross entropy function here, which assumes 2 class labels. So 2 possible class labels. Here, since we want to fool the discriminator, so we want to fool the discriminator, we want to force it to make a wrong prediction. And we talked about flipping the class label for that. So here, should maybe say we also run the discriminator forward method. So the discriminator is just a binary classifier that outputs the probability that an image is real. So we give it here the generated image, which we generated here. So this is our x prime. I'm just reshaping it here to the right shape. So here I'm generating x prime. I'm using x prime and giving it to the discriminator. And the discriminator, if it's a good discriminator, it will detect that these are fake. So it will output a 0. And if it's a good generator, it will fool the discriminator. So if the generator is good, the discriminator will think it's a 1 here. And we can make the generator learn to make such predictions by using this loss in the optimization method, in the optimization part, and valid this corresponds to the class labels of the real images. And again, we use here the trick that we flip the class labels so that we minimize the cross entropy. So this is now class label 1, although it's a fake image, right? So we flip the class label, and we want this one to be 1 because we want the discriminator to think that this is actually real. So here we just minimize the cross entropy, which is similar to just a regular classification problem, except the trick was here that we flipped the label. And for reference, if it's been some time since you saw the binary cross entropy function, recall from the logistic regression lecture, this is just minimizing, or this is just a negative log likelihood. So that is the cross entropy for the binary case. If that is maybe still a bit confusing, I recommend maybe just going back to lecture 8, but also feel free to ask questions on Piazza like always. Okay, now that we talked about the generator, let's talk about the discriminator loss here. So we want here the discriminator to become also better at recognizing fake images. Before we wanted to fool it when we updated the generator. Now we want to improve it because we update the discriminator itself. So for that we have to run the discriminator 2 times. The first time we run it here on the real images. So these are X or the real images. And here we now also have again the class label, the ones. And here it's correct because these are actually real images. So in the ideal case, this discriminator should learn also to predict a 1 here. That would be good to output a 1, so a very high confidence that this is actually a real image. And then the second part is we want to also recognize fake images. So we run the discriminator a second time, but now we give it the generated features. So the generated features are X prime the fake images. And here we also provide the fake labels, so that is the zeros. And we hope that it also outputs a 0. That means it correctly recognizes that this is a fake image. And then for the loss, we can combine the 2 parts. So we have the real loss. The real loss means the loss on the real images. And then the fake loss means the loss on the fake images. And we can just add them up together and we can optionally average them by multiplying by 1 over 2 or 0.5. Yeah, unfortunately, I just see we only have 5 minutes left in that lecture. However, luckily we are almost done with the code examples. So let me keep that a little bit brief here though. So what we have here, that block, is the generator part that we talked about before. And in this block, we have the discriminator part that we talked about before. So there's nothing new here. What's new here is this part and this part. And here I'm just using optimizers to update the generator and the discriminator. So here, that is also the usual cascade of updating. So we start by resetting the gradients from the previous iteration, and then we apply backpropagation, and then we use the gradients to update the weights. So these 3 usual steps. But the main part I really want to highlight here about that is that we want to use different optimizers for the generator and the discriminator. We can both use the same type of optimization algorithm like Adam or SGD, but we want to initialize them separately. That is because when we run or when we optimize the generator, we only want to update the generator parameters. So we are very specific in that we only give this optimizer the parameters of the generator, so it doesn't update the discriminator in that upper part here. And then in the same way, for the discriminator optimizer, we only provided the parameters of the discriminator. So for that part, we don't update the generator, and with that we can make sure of that. Also, if you like, you can use different learning rates, which is sometimes necessary to get good equilibria when we train the GAN. So now I'm going to show you some GAN examples, so examples of GANs that I've trained on MNIST. So for your reference, these are MNIST images, which you have seen a lot of times in this course, but just to recall how they look like. So my first GAN is here. I was training a fully connected GAN, so I was using a multi-layer perceptron GAN, where the generator and discriminator consist of fully connected layers. You can check the code examples here if you want to see more details. But yeah, what I'm seeing here is that the generator and discriminator loss, they kind of converged. So you can see the generator starts fluctuating a lot and then it converges here, and then the same with the discriminator. So they kind of converge at some point. However, the images don't look very great. If I look at the generated images here, so these are new images generated by the generator part of the GAN. They don't look very good. And I would say that's mostly due to the fact that this is a multi-layer perceptron GAN. So it's not very good at working with images. So what I did then is I tried to implement a convolutional GAN using CNN parts, so convolutional layers in my GAN. However, what I saw is that this converged, but yeah, what came out of it was pretty much, yeah, garbage here. So this one failed, it didn't produce anything useful. And like I said, it's not super easy to train again. You have to try multiple times to find the right settings. So I tried again, tried to train a convolutional GAN here, and what I saw here was the mode collapse I mentioned before. So it looked like it trained relatively well, didn't really converge. I think it's going up here. It looks a little bit weird, but it doesn't look too bad, and it is actually generating images. However, it's only generating images of the same kind, so it suffers from the so-called mode collapse, where it can only generate images of one kind. It doesn't explore the data distribution in full. Next, I tried harder, and I got a convolutional GAN to work, which had some weirdnesses here, some oscillations here. However, it was, in the end converging. At least it looked like it converged. But again, I was not really happy with these images. So I did some more tuning, and somehow I couldn't get it to work really. So one thing I tried then was using batch norm. So I just added batch norm to it, and now you can see it doesn't look too bad actually, right? So these look almost like real images. And lastly, I tried to improve that further, and I used a trick called label smoothing. So I replaced the class labels of the real images, the ones, by 0.9s, which is an idea proposed in this paper here. Fortunately, we don't have that much time anymore to talk about this in detail, but you are welcome to check out the paper. And here also it looked like it converged, and I like the results in this one much better than previous results. I mean, not much better, but compared to the previous slide, I think this improved a little bit. So the label smoothing might be also a good idea. So these look like real images, I would say. I mean, at least real MNIST images. So I then tried to use the architecture previously implemented for more interesting data sets, like images of cats and dogs or face images. However, it didn't work quite well, so I just used a simple convolutional GAN from literature that has been proposed like 5 years ago. In terms of GANs, it's like pretty old, but I think it's a pretty good starting point to have some relatively simple architecture to start with. And in this particular GAN, they use a 100-dimensional vector, so the Z vector has 100 values in it, and the output image is 64 times 64 times 3. So because 5 years ago this was a really, really big image, 64 times 64. And yeah, so that is the generator architecture that I implemented. So here are some results. I was using that cats and dog dataset from Kaggle. So in this code examples, I have instructions for downloading the dataset and also the whole GAN that I implemented there from the paper. And here what you can see is the dataset is pretty diverse. So they're all different backgrounds and things like that. So of course they're all cats and dogs, but some of them are photographed from the side, some very frontal and so forth. So there are very different poses here even in the image. So it's kind of challenging for a network to generalize from that, especially if that's a very small data set. And I think it was only 50K. So for such a complex data set, 50K is actually relatively small. However, when I then trained the GAN with some hyperparameter tuning, I could see that it was actually learning something. So in the first iteration, the outputs looked like that. And then after a few iterations, it improved. So it looked like that and then like that. And in the end, I got results that kind of looked interesting. I mean, this is maybe a dog, but maybe don't look at it too closely because I think that will rather generate nightmares. But yeah, it was learning something here from the training set, not exactly animals, more like bizarre shapes. But that is also because the dataset is maybe too diverse and there are many different types of poses in the dataset. We would maybe need a much larger dataset to learn well from that one. So I then tried the CELAP-A face image dataset, and here on the left hand side there are images from the training set, and you can see they are, I mean, of course, all centered here, so that is a little bit easier for the GANs. So the backgrounds are still different, but the images are centered, and the dataset is also much larger than before. I think it's 5 times as large as the cats and dogs dataset. And as you can see here on the right side, the GAN, I mean, produces some good images, so I would say this is a pretty good one. This one, maybe this one. There are really good results among these images here. And also I should say, in practice, when you see GAN papers, usually what people do is they cherry pick the results, so they don't show you all the results, they show you some of the good ones. So here I would say this is actually pretty successful, so there are a lot of people who look like real people, although they are not real. So that is actually pretty cool, I think. So lastly, because we really don't have time anymore, let me just briefly recommend to you some resources about GANs. So there was a GitHub repository that listed all the named GANs. So there's a huge list of GANs. It's a little bit small to see, but in 2018 or 2019, there were about 510 different types of GANs. So there's a huge number of GANs. Unfortunately, that GitHub repository here is not updated anymore. I think the last time they updated it was like 2 or 3 years ago, but I think it's still a good starting point for seeing what different types of GANs exist. If you're maybe interested in a particular one, you can find also the links to the papers here. So personally, if I had to pick 3, I would go with the Wasserstein GAN, the cycle GAN, and the conditional GAN. So the Wasserstein GAN is changing the loss function using the Wasserstein distance. The cycle GAN is the one with the cycle consistency that I showed you in the very beginning with the zebras. And the C-GAN, the conditional GAN, is modifying the GAN such that you can incorporate a class label in the training procedure, because originally GANs are unsupervised, but if you use a class label, you can then also later sample using that class label. When you generate new images, you provide the Z vector and the class label of the class you desire, and then you can generate, for example, specifically dogs or specifically only cats and so forth, which is also very useful in certain applications, especially if you have a data set with a lot of classes. This way you can select which classes you want to generate from.